Okay, this is the part 2 of chapter 5, and we're going to talk about gravitation at this time. First, let's talk about Newton's law of gravitation. So we have the Earth, we have the force of gravity on people all around the Earth, and they're all pointing towards the center of the Earth. So Newton thought about what keeps the moon in orbit. He was observing, of course, the moon. This was in the 1600s. So, for millennia before that or two, then, of course, they observed the moon. So he thought, well, maybe it's gravity that keeps it up. So his thought was that if the gravity that affects an apple in a tree, it might also be what affects the moon. So he did some observations and such. He didn't really get hit in the head with the apple like some of the cartoons show you. Okay, so we're going to look at what Newton's law of universal gravitation is. So he looked at the moon and the Earth, and he wondered that maybe there was this force, equal force between the moon and the Earth. And from the moon is the gravitational force exerted on the moon by the Earth. And then there's also, the result of that is it goes around in a circle, and the gravitational force exerted on the Earth by the moon, of course, we see the effects of that in the tides. So all this is to form the universal gravitation. You will not be responsible for knowing all these details. So sit back, listen, and watch. So it can be shown that the moon centripetal acceleration is 0.00272 meters per second squared, which happens to be 1/360th of the acceleration due to gravity. 360 or 3600, I think I said that wrong. 3600 is actually 60 squared. So it can be shown that the centripetal acceleration is 1/60th squared of the gravitation of universal gravitation, 9.8 meters per second squared. Just so happens that the distance is about 60 times that the radius of the Earth. So this is not drawn by scale by any means, because one radius right here, but you'd have to count out 60 of them, and it would be way off the screen on that. So it's been shown that that gravity is proportional to 1 over the radius squared. That's where this is coming from. And that the force is also directly proportional to the mass of the object and the mass of the Earth. So that means that the force is directly proportional to the product of the masses. I think that I was supposed to type in an M there. I don't know why that says B. Just ignore that for now. And the force is also indirectly related to the square of the radius. So he came up with the conclusion that it's the same with the sun and the planets. And so here is his formula for universal gravitation, which states that the force due to gravity between two masses is equal to this G constant, which I'll talk about in a minute, times the product of the two masses involved, could be the sun and the Earth, for instance, divided by the square of the radius of the orbit. So this is R is going to be the distance between the two masses. Okay, so it wasn't until Henry Cavendish came along and he actually measured. So by showing that this is proportional to the product and proportional to the indirectly proportional to the square of the radius, the big G was unknown until Cavendish came along, and he measured the universal gravitational constant and got this really weird looking number. Sorry, let me go back to that. is 6.67 times 10 to the negative 11. The units come about because if you solve this equation for big G, then the product of the masses become a denominator over here. And so that's why we have kilograms squared. And the radius squared would become a numerator. And so that's where we get meters squared. And then, of course, the force is measured in newtons. So we don't put these units in our calculations. We simply take the value of 6.67 times 10 to the negative 11, and we're going to put that in the value. So with this, we can calculate the force between any two masses, whether they're planets and suns or stars or galaxies or actually even people. So let's do an example. Pause the video so you can go ahead and see what you can do with that, and unpause it when you need to. So we're going to calculate the force between the Earth and the Moon. And the facts are the Earth mass is 5.98 times 10 to the 24th kilograms. The Moon's mass is 7.35 times 10 to the 22nd kilograms. And the distance between the centers of the two, the Earth and the Moon, is 384,400 kilometers. So we're going to use this universal gravitation formula, and we're going to put these values in. So you can go ahead and do that. Pause the video. So here we go. So the universal gravitation constant, 6.67 times 10 to the negative 11, goes here. The mass of is arbitrary, which one you put first. So we're going to put the Earth first, 5.98 times 10 to the 24th. And then 7.25 times 10 to the 22nd in here. And then notice that what happened to the distance between the centers. It's stated as 384,400 kilometers, but the universal gravitation constant, remember, has a meter squared in it. So we have to change that value to meters. So we put 384,400,000 meters, and then we're going to square that. So to put this in your calculator, you should use the E button. And if you're not sure how to do that, then either Google that or ask me in class, and I'll show you how to do that. So you can pause and see if you can calculate that. And the result is 1.98 times 10 to the 20th newtons. Now you have no relative measure for that. That really is a very, very, very large number. It's 1.98 with 18 zeros after it. So it's a huge number, but then again, we are talking about the force between the Earth and the Moon. In a sense, you could say that's what the Moon weighs, because most of the force is coming from the Earth. Okay, so the question is there gravity between people? Well, yes, because two people have masses, they have a distance between the two, then you could actually calculate it between you and someone else. But it's very small. We'll do that calculation in class, or maybe you can play around with that and figure out if we had two people, say 100 kilograms, on what that force between the two would be. So here's another question. Where would you have to be to not have an attraction between someone? So let's say you calculated this very small force. The further away you get, of course, the smaller the force, but there's no place you can go where the distance is going to cause the force to be zero. So that means anywhere you go in this universe, you're going to have an attraction between you and that person, which also means that there's a force of gravity between you and every piece of mass in the universe. Blew your mind on that one, didn't I? Okay, so we're going to talk about gravity near the Earth's surface. As I told you when we introduced the acceleration due to gravity, I told you that it's 9.8 meters per second squared on the surface of the Earth. But what happens when we move away from the the surface of the Earth, either towards the center of the Earth or away above the Earth. Well, acceleration due to gravity, little g now, varies with the distance from the center of the Earth. So we will be able to calculate that using this universal gravitation. So for us to do that, we take the weight, which is mass times gravity. We set that equal to the universal gravitation formula, big G, mass of the object times the mass of the Earth, divided by the distance squared between the center of the Earth and the mass, which is on the surface. Notice that they both have mass on both sides, so we can cancel that out. And we get this formula to calculate the acceleration due to gravity, knowing the mass of the Earth and the distance away from the center. Now keep in mind, if we wanted to do the acceleration due to gravity of Mars or something, then we would use the mass of Mars and the radius of Mars, of course, or whatever body we were doing that. I guess you could even calculate the acceleration due to gravity on the surface of your head if you really wanted to, but we won't do that. Okay, so big G was then used, the one that Cavendish found. He used that, and they actually now able, or at that point, was able to calculate the mass of the Earth. Before it was, they used the density formula to calculate the mass, knowing the average density of the Earth and the volume of the Earth, and then they calculate a mass. But this way, they're using physics in this sense. Many other things affect the acceleration due to gravity besides the distance from the center of the Earth. Things like the rocks that you're standing over, or mountains or valleys, and so all that adds up to gravity. As we learned from universal gravitation, there's gravity between any two objects. So let's for a second go ahead and take this formula and let's put in the values for Earth. So we have 6.67 times 10 to the negative 11. That's the universal gravitation. We have the mass of the Earth, which we looked at earlier, 5.98 times 10 to the 24th, and then divide that by the radius of the Earth, which is about 6,371,000 kilometers, or meters rather, and then we square that and magic happens and it comes out to about 9.8 meters per second squared. So pretty astounding that in laboratory we can measure it using kinematics, and now with dynamics we can actually calculate it and it comes out to the same thing. Okay, so let's try an example problem. What is the acceleration due to gravity on the International Space Station that is orbiting at an altitude of 385 kilometers, which is about 240 miles? Now, this is an altitude, so we have to pay close attention to that. I only told you the 240 miles just so you have some sort of reference. It's about the length or the distance of I-5 in Washington. So that's how high up the International Space Station is. So given the mass of the Earth and the radius of the Earth, we are going to plug this into our little g calculation. So we put universal gravitation constant in there, the mass of the Earth in kilograms, and oh, watch out, we have the distance now is a little bit more complicated because this is the radius of the Earth, and it's in kilometers. So the first thing we switch that to meters. And then we're not going to just use that because we're now also 385,000 meters above the surface, so we have to add the altitude before we square that unit. You can go ahead and pause the video and do that calculation and see what you get. So that comes out to 8.74 meters per second squared. Well, that's not very much less than 9.8, is it? Let's go ahead and calculate the weight of a 90 kilogram astronaut. Seems reasonable. On the International Space Station, we take the 90 times that 8.74, and we get 787 newtons. Just for reference, on Earth, using 9.8, it's 882. So it's not that the astronaut is weightless. Well, it's true, he doesn't weigh as much, about 100 newtons less. But as you know from the work in class, 100 newtons, really not that much. So why do we call it weightless, by the way? Maybe we'll figure that out in later lessons. Okay, so thanks for listening. If you have any questions, contact me in the usual sense. All right, thank you. Bye.